All right, here we are with video. We're going to talk about second order partial derivatives. And instead of just doing, you have some of these problems to do in my math lab. They'll just be asking you to compute these second derivatives or second order partials. What I'm going to do is I'm actually going to do kind of two things at one time. I'm going to show you how to do this or give you examples of how to do this in the context of finding extrema for a given surface. Okay, so that would be maxes and mins, and then there's going to be something we'll refer to as a saddle point. Okay, so so we'll be doing a lot in this video. Again, please use pause and scroll in order to, maybe go back over something that may seem a little quick for you. All right, so the first thing, partial derivatives. Basically, it's similar to what we were doing when we had one independent variable. You're just taking the derivative of the derivative. And so this notation here, this will be the second partial derivative with respect to x. And we're going to take that function z and take the derivative with respect to x, and then take the partial with respect to x, and then take the partial derivative with respect to x with whatever's left over of that expression, okay? And we'll do the same thing only with respect to y. So this notation here or this notation here or even this one all mean the same thing, okay? And that's pretty straightforward, I think. As far as the mixed partial that I have over here, what you're going to see is that the first thing we're doing is taking the partial derivative with respect to x, and then we take the partial with respect to y. This gets a little confusing because it looks like the order here, makes sense, right? We're gonna take the partial with respect to x first, and then y, and that kind of makes sense. But over here now they're writing that as xy. So again, it's on the, I guess the y is on the right-hand side here, and that can be confusing. But over here, again, this is the mixed partial, first with respect to x, then with respect to y, okay? Now, the good thing about this is if I go in the opposite order and take the first partial with respect to y and then to x, at least for all the functions in this that you're going to be dealing with, these two mixed partials are always going to be equal. So I'll mention that in the example as well, okay? So that's the first thing, all right? So we're talking about second order partial derivatives, all right? I will give you examples within the context of finding maxima and minima, all right? Now, I don't want to get too bogged down into this explanation here. I just want you to see the graph of an example of a relative max and a relative min. And again, we're talking about locals here, okay? So these surfaces could, for instance, come out here and then go back up or something like that. So we're looking for mounds that are, maybe, upright or inverted, okay? And obviously the high point on a mound is going to be the relative maximum, and the low point in a, like a base or a cup here is going to be the relative minimum. And where that's going to occur is, remember the partials with respect to x and y, we're going to be looking just like we did with one independent variable, wherever those slopes of those tangent lines are equal to 0, or in this case, parallel to the xy plane. Now, when we go ahead and take a look at these, again, finding these tangents, this is going to be a process, and it's going to be similar to the second derivative test that you've already done with one independent variable. There's one other thing that can happen on these surfaces when you find a critical number, okay? So this AB is going to be a critical number. It's where, again, the partial with respect to x and the partial with respect to y are going to be both equal to 0. But there's one other phenomenon that can occur, and it is a saddle point, okay? So again, this kind of looks like a horse's saddle. Somebody would sit in there, if you were riding on a horse. And it's where a critical number can occur here at that point, that particular point. Okay. And, just remember, like when we were taking a look at f of x equals x cubed, I know I don't have the graph here, but we had a tangent line equal to zero, but there was no relative max, nor there was a relative min. The same is going to occur here. This is not a relative max, nor is it a relative min, because it doesn't have that mounding effect. And that's probably the easiest way to describe it, like we have here. Now they're talking about this open interval about it, and that would be like just the space around it, okay, that we're going to get an absolute top of a hill or a bottom or a peak of a valley here. That's not occurring here at a saddle point. We don't have that area around it, okay? We got it going up in this direction, up in this direction, but down immediately in those, I guess you could say maybe 90-degree directions, okay, from that point. And so we refer to that as a saddle point, just like I guess in the X cube was the inflection point, okay, where the graph changed concavity. So how do we do this? Well, I got a couple examples following here, but this is the basic procedure, okay? The first thing we're going to do is we're going to find the critical uh, numbers, okay, or critical points. And where that's going to occur for x and y is where the partial with respect to x and the partial with respect to y are zero, okay? That's where those tangent lines would be zero. Now, once we find those, then we're going to compute this discriminant. And what we need to do is evaluate the second partial with respect to x at that critical point times second partial with respect to y at that point, and then subtract the mixed partial. Okay, again, doesn't matter which one we find, x and then y or y and then x. Doesn't matter, they're going to be equal to one another. And we're going to square that value and simplify this expression. And we're going to get a value for the discriminant, or d. If the d is positive, okay, all right, we are going to have a relative minimum or a relative maximum, okay? That's in both cases, d is going to be positive, okay? We can have either a relative min or a relative max. How we know which it is we take the second partial with respect to x and evaluate it at that critical point. And if it is negative, then we know we have a relative maximum, okay? If that second partial with respect to x evaluated at that critical point is positive, then we know that we have a relative minimum at that point, okay? Now, we can have a saddle point, okay, if the discriminant is less than zero, okay? So, we would stop and not evaluate the second partial if the discriminant turned out to be less than zero. And if it's equal to zero, then the test gives no information, and then we have to rely, on the graph or some other method here, which we're not going to discuss, okay? So, I'm going to go over this examples. I'm going to give you examples of finding a maximum or a minimum, and then saddle points, and then we'll go ahead and see what happens after that. Okay. So I have here a couple of examples. I'm just going to go through this because I picked these out of these notes that I've used before. And we're going to take a look at this number 3. Okay. So if I could find that one, I think that's right here, if I'm not mistaken. No, that's not it. That is going to be this one. Okay, so let me go back here to my Inspire just to show you. Okay. Oh, no, it was the other one. Here, let me get that. Yeah, here's number 3. Okay. So let me go back to that. Okay, so we have this function here and it says find all local extrema. All right, so this is kind of, I threw this graph on here just to show you these points, or point, I guess. And I'll do this again in the live graph. This is just a captured image here showing you the point, but there's no local maximum, okay, or maxima, which would be more than one maximum. No local minimum, Okay, so you would just select that, and then there's a saddle point. Okay, and there's actually one saddle point here at 0, -12, 1. You can kind of see that little point right here, and I'll show you again on a live graph here. Okay, so how did I find that saddle point? Well, let's go ahead back here and take a look at this particular multivariate function. Okay, so the first thing I'm going to do is find the partial with respect to x, and then find the partial with respect to y. Now, this is a relatively simple one to do. It looks complex, but remember, the derivative of e to the x is just e to the x. All right, so I have to use a chain rule here. So I have my composition of functions. So the derivative is just whatever this is times the derivative of this with respect to x. Well, again, since y is a constant, right, and this is also a constant, then that's just going to be 1 times whatever this is, okay, which is y plus 12. So I have y plus 12 times e to that exponent. In a similar fashion over here, I'm going to do the same thing, only now I'm taking the partial with respect to y. So again, it is just going to be this thing right here, okay, this thing right here, times the derivative of this expression here with respect to y. Now remember, we just treat x as a constant. So if we looked at this maybe as the product rule, right, derivative of the first, which is going to be 1, oh, I'm sorry, is a constant, which would be 0 times that, plus the second derivative of the second, which is going to be this, which would be 1 times the first, which is just going to be 1 times x. So we end up with x times this thing right here. Okay, so you may want to replay that again just to get the derivative. I know that it's kind of quick, but we're just using the chain rule, and we're treating y over here as a constant, and over here we're treating x over here as a constant because, again, these are partial derivatives. Now, to find the second derivative, well, I am just going to go ahead and, again, since this is a constant, right, I am just going to go ahead and take this thing times the derivative of that exponent. Well, we already did that up here, right? The derivative of that exponent using the chain rule is just y plus 12. Okay. And I'm going to do the same thing over here, right? Because again, I take this thing, all right, I'm treating x as a constant, so it's just constant times e to the whatever it is times the derivative of that exponent using the chain rule. So we already did that up here. It's just going to be x. So I have x times x, or x squared. Again, you may want to replay that, pause and replay just so you get that derivative down, but that's the second partial with respect to y. Now, the mixed partial, if I take the derivative first with x, okay, and then with respect to y, so I am going to be working with this function right here, okay? So what I'm going to do is I am going to go ahead and go through this process, right? Okay, so I have the derivative of x, and now I'm taking the derivative with respect to y. Okay, so I'm working with this thing up here. So the derivative of y is just going to be, I have to use the product rule, right? Because I'm taking this as one factor and this as the other factor. Well, the derivative of this with respect, again, to y is just going to be 1, right? Times whatever this thing is, okay? Then I take plus the derivative of this, right? Okay, I'm going to take this times the derivative of this, again, with respect to y, okay? Well, I already did that up here, right? So I just need to go ahead and take the derivative of y over here, right? Okay, and multiply by the or I'm sorry, excuse me, I take this thing right here times the derivative of this with respect to y. So I already did that over here. Sorry about that. So I'm just taking this times first times the derivative of the second, which is going to be this thing here, okay? So then this is where it kind of gets a little bit tricky, okay? So again, you may want to play that. All I'm doing is using the product rule here, okay? And within using the product rule, I got to use the chain rule, but I'm using some of the results from above. Now, what I need to do is I look here, I want to simplify this expression here, and I get the a common factor of e to the x times the quantity y plus 12. And I see that that's common to both factors. So I'm going to go ahead and pull that out, and I leave behind a 1, and I leave behind a y plus 12 times x. Okay, so now I have this thing simplified. So now I've got all the partials that I need. Partial with respect to x, partial with respect to y, second partials with respect to x and y, respectively, and then the mixed partial here. So now a little bit more work here. Okay, again, these are pretty intense. And so what we need to do is find out when the first partial is equal to 0. Well, all I need to do is set this equation equal to 0. Now I know e to whatever is, I know an exponential function is never going to equal 0. So really, the only time this equation could be equal to 0 is when the y plus 12 is equal to 0 or y equals negative 12. So these equations aren't too bad to solve, okay? This partial over here, in the same way, this is never equal to 0. Okay, it's always going to be something no matter what x and y are. So the only time this whole thing's going to be 0 is when x is equal to 0. So my critical point is going to be x equals 0, y equal 12. I am now going to substitute it into these expressions. I'm not going to take time to go ahead and explain that, but basically I'm just coming up here and I'm replacing x and y, okay, with 0 and negative 12 respectively. Okay, I'm going to put that in here. Well, I get 0 when that happens. Okay, that's pretty easy actually to figure out here because like what I have over here, when I put negative 12 in here, I'm going to get 0, and I don't care what anything over here is. All right, and the same thing over here when I substitute in x. And so these two things are going to be equal to 0. And then the partial with respect to y, again, if I again just substitute in x equals 0 and y equals negative 12, I'm going to get 1. Well, when I simplify all this in here, I get a negative 1. And if you remember what our criteria says, is that if we go back and take a look at what it's saying is that whenever we get the discriminant less than 0 or less than 0, we know we have a saddle point. Okay. And so all we need to do to finish that up is to just go ahead and find the z value. And I just substitute in 0 and negative 12 in the original equation. And when that happens, I get 1. And I'm not going to go over all those substitutions. I think you guys can do that, substituting in, again, these values in the appropriate equations. And same with this. This goes in the original, and that's where the 1 is coming from. So now, when I come over here, just to show you, when I graph that function here, okay, I need to go ahead and find the right one here, and I already had this. So here's my function, and here's the point negative 0, negative 12, and 1. And notice as I'm moving this around here, you can see, I guess the coordinates are kind of blending in there, but you can see that saddle point here, okay? And if you always want, and this is a good way to check your work before you submit it, go ahead and actually look and see, make sure that there appears to be a saddle point here. The one thing that you might have to do, when you have this default area is to go in the settings, and you may have to manually adjust your axes. Okay, over here I had to adjust the Y min, and I'll show you here in a second, because if I use just the default values to find the graph, it's not going to plot on there because they're not set up automatically. I had to stretch this out to negative 20 for my Y min in order to see it. Okay, so I'll show you that here. If I did the home, you can see that that point is not on, doesn't appear to be on the graph, and it looks kind of weird here because it's kind of sitting out here in space because the graph isn't plotting in the right spot here because it's got to go out to negative 12, and my axis is only going out to negative 9, my y-axis. Okay, so that's the reason why. So I'm going to leave this graph here. Again, rewind it just so you can see it, but it is indeed a saddle point. Okay, So if I could go back to my kind of move ahead here to my next example. Okay, so I just did that one. Here is this function here. And notice there's no local maxima, but there is a local minimum. And again, they're not asking you to find the z, they just want the x and y value. Okay, just the ordered pair. Okay, and there is a saddle point. So this graph here is going to have two of those sections. Well, when I go ahead and do this, I am going to go ahead. Okay, so what I'm going to do is, sorry, I had to take a little break there. There's a noise, background noise. And I'm going to go ahead and go through this process here. This one's a little bit different, finding the critical numbers, but not too bad. Okay, so here again, finding these derivatives are pretty simple. Now I've got something that, it's just like a polynomial here. And I want to go ahead and take the derivative with respect to x for my first partial. Okay, so going ahead and doing that, I get 16x here. I get, I treat y as a constant. That's a constant, so that would be 0. And so I'm going to get 24y here because the derivative of x is 1. Okay, so that's my first partial. Taking the second partial with respect to x is pretty simple. I just get 16, right? Because the derivative of this is 1, and that's, again, a constant. Over here, very similarly, I do the same thing. I'm going to take this derivative here, so I get 0 and 0 here, and I get minus 24x. But over here, again, for y, I am going to get 3 times 3, and then subtract the 1, and I get 2. And then likewise over here, just like over here, I treat this as a constant. I get 18y for my second partial, okay? Now, for my mixed partial, it doesn't matter. If I take this and I take their derivative with respect, first with respect to x and then to y, notice I get negative 24. And same thing over here. If I take derivative of y with respect, or derivative of y first and then x, I'm still going to get negative 24. Okay, so either way, I'm getting negative 24. Okay. And now I want to go ahead and find out when the first partial is equal to 0. So I go ahead and set that equation equal to 0, but notice I really can't solve it. It's a linear equation, has infinitely many solutions right here. But then again, I have to consider where the first partial is equal to 0, so I've got this quadratic. Well, this is basically a system of equations, okay? So if I take this one and solve for x, and then substitute it into this one. This is just an algebra 2 problem. In other words, I'm replacing this x over here with, this simplifies to just 3/2 y, and then I'm not going to go through all the details here, but basically I factor that down here and get this quadratic and then solve for y. I get two different values, 0 and 4, all right? So when y is equal to 4, I just substitute back in and I get a value for x, which would be 6. And if y is equal to 0, I substitute back into this and I get a value for x, and it's going to be equal to 0. Okay. Now, again, I'm not going to go through all these substitutions because that just gets long, and I don't know. I think you guys are able to do this. I just go now to my second partials and I substitute in those critical points, 0, 0, and I take the product, okay, and I get 16 times 0, and then I substitute into the mixed partial 0, 0. I get negative 24, and when I simplify all this, I get a negative value, which tells me I got a saddle point at 0, 0. Okay, now I'm just putting the 20 so we see the graph. I take my 6, 4. I substitute into the appropriate partials. Second partial with respect to x evaluated at 6, 4. The second partial of y evaluated at the 6, 4. And then what I do is I know that kind of looks like an x there, but that should be a y. Okay, that's the second partial of y. And then I substitute in the mixed partial here, and I get a positive value. Okay, so when I simplify all this stuff out, multiply it out, and again, you got to be careful. That's why I want to use brackets and parentheses and so forth. So I got to square this thing, but I still subtract it. But this value over here is greater than that one. I get a positive value. And so therefore, since it's greater than zero, okay, my second partial evaluated at 6.4 is greater than zero, then I have a minimum. Okay, so I'm going to go back here just to show you that criteria real quickly. I'll just go ahead and do that. Okay, so here we go. We just got to go back to this chart, right? Okay, so again, the first thing is my discriminant's positive, right? And then I evaluate the second partial with respect to x at that critical point, and it's less than zero. Therefore, I have, or I'm sorry, it's greater than zero. Therefore, I have a relative min there. Okay. The, that one. Got so many things opened up here. Let me see if I can get back there. Okay, here it is. Yeah, it's greater than zero. Therefore, I have a relative min. Okay, that second partial at 6.4. All right, so let's go ahead and take a look at that one. I graph the function, I graph the point, okay, the saddle point, and I also graph the minimum. And you could see that the minimum over here is at 6.4, negative 76. I substituted in just the original equation. I put the 6 and 4 in for x and y, and I got z equals negative 76. And the same thing with 0, 0, and 20. That one was easy to find, but there's your saddle point up there, okay? And so you can see that. Okay. And again, if you want to do this, like I said, I think it's a good way to check your work. Okay. Um, a couple things here. Number one, I just, you don't have to do this, but you plot the point. Sometimes you have to change these settings. Sometimes it comes up just showing the name of the point. Okay. I'll just go ahead and select that. Notice the coordinates are not there now. Okay. But if I go back again and change that back, I can go ahead and display the coordinates as well. Okay, so yeah, so the name and the value, I can turn the coordinates back on there. Okay, um, so that's one thing. And the other thing is, again, you've got to be careful here. Notice how I had to change the settings of the graph here. I had to make sure that my z-axis went all the way down below negative 76 in order to see the minimum value. And I had to go up here because this was a 20. I just went up to 30 just to make sure that I could see that saddle point. Okay. Um, I'm going to go ahead and hit the home button here just to show you what the default window was. And you're not going to be able to see any of these points in the graph, and it's going to look very weird. Okay. And that's just because, again, if I look at the window here in settings, notice it's only going from -9 to 9 and on the z-axis, -3 up to 6. Okay. So, you have to manually change those. And again, just scroll back and rewind if you want to see the graph again. But like I said, I know takes a little bit to become familiar with the software as well. So I know this is a long video, and but there was a lot to explain. And as long as the video is, that's only 2 examples. I know you have more than those to do, but again, I hope this helps as usual. And let me know if you have any questions.